Hey guys, in this video we're going to cover what binary search is. And binary search is also known as lexicographic or dictionary search. Now why binary? Binary means consisting of two parts, right? So either zeros and ones. So in this binary search, we're going to divide the list into two parts and search. So imagine searching for a word inside a dictionary containing thousands of pages. Would you start from page 1 and then check through every single page one by one? That would take more time, right? So we don't do that. Instead, you directly jump somewhere near the middle. Then, based on what you find, you eliminate half of the remaining pages. That leaves you with just half. So it reduces a lot of time and effort to look for that particular word in the dictionary in this method. So the binary search algorithm works in a similar way. It works by checking the value in the center of the list. If the target value is lower, the next value to check is in the center of the left half of the list. So this way of searching means the search area is always half of the previous search area, and this is why binary search algorithm becomes so fast. This process of halving the search area happens until the target value is found or until the search area of the list is empty. So binary search is much faster than linear search but requires a sorted list to work, right? Unsorted lists in this case would not work. And in this video, we're going to understand what binary search actually is, why it is extremely fast, how the algorithm works internally, the time complexity analysis, and the complete Python implementation. So we'll also visualize the entire process step by step using diagrams and dry runs so that the logic becomes crystal clear. And there's also another way of implementing binary search through a recursive algorithm, which follows a divide and conquer approach to solving problems, right? Just like the way we are doing here, but in this method we're using a while loop to loop through the entire list and find the mid value. But in recursive algorithm we call this binary search function again and again till we find the mid value. So that is the difference between the recursive algorithm and the normal algorithm that we have right here. And it divides the data, checks one half, and then applies the same logic to the remaining relevant half. So let's begin by understanding the intuition behind binary search. So on the right side we have a dry run of the entire list, but before we come to this dry run and this entire sorted list, I would like to first explain the part where we are giving that input, be it an unsorted list or a sorted list, right? And if we give an unsorted list, then this algorithm that we have right here, the isSorted method, is going to check whether that list is sorted or not, and if it is not, it just gives us a sorted list, and that is the list that we pass to binary search method. So here I have a class binary search, and inside the default constructor I have numbers, a list of integers that we have initialized, right? And inside the main method I have an object created of the type binary search class, and here we have a tuple where I have called the user input method. Now the user input method returns us a tuple which is containing a list of integers and an integer, right? Now I'm going to open this user input. Now in this line we have a list of strings that we're taking as input, or not a list of strings but a whole string initially, and that whole string is what we use to split from the spaces. So after having split from the space that we have taken through input, we're going to use the map function to convert each string value that we're going to get into an integer, and when we convert them to an integer, we're going to get a mapped object of every integer value. So we're going to use the list function here to convert the mapped object of every integer to get a list of integers, right? And we're going to convert them into a list and store them in the numbers variable, which belongs to the class. And then we take the input for the target, convert them into an integer, and pass it as a tuple and receive it right here in line 39 as numbers and target. So in numbers we have the list, and the target we have the integer, which is what we are returning as a tuple, right? Now thereafter we have called the isSorted method, which is passing a numbers list, right? So inside isSorted we have the numbers list of integers, and it is also returning a list of integers. So no matter what, is going to give us a list of, we're going to pass a list of integers and we're going to receive a list of integers. But the difference is, what we're going to send and what you're going to receive is, we're going to send an unsorted or sorted list, and it's going to check whether it is sorted or not, and it's going to give us that same list but in a sorted manner no matter what. Even if it is sorted, it will still give us that same list. And then we run a loop through that list from 0 right through the last of that list, the last index of that list, and we check if the current number is greater than the next number or not. So we check if they are in ascending order or not, right? The code for binary search would have been different if this was in a descending order. And we check if they are in ascending order. If it is not, we just say that it was not sorted and we sort them. So in line 15 we have numbers.sort. So in Python, the sort function here is using the timsort algorithm, right? I'm not using bubble sort or insertion sort or quick sort to enhance the speed of this execution, because my focus here is mainly on the binary search algorithm. In the next few videos, I may even come to quick sort, merge sort, insertion sort, and explain all those algorithms. But in this one, we want to focus more on binary search. So I've used the timsort algorithm by default, which is built-in method or function for Python. And timsort algorithm is also a hybrid between merge sort and insertion sort. Ultimately, we get the sorted list and we return the numbers, right? And if they're already sorted, we just say that this is already sorted and return the numbers anyhow. Now, after isSorted is called, we receive that numbers in a sorted manner, right? So numbers now has a sorted list, and then we call the binary search method and we pass the numbers and the target. So in binary search, when we have the numbers, the sorted list and the target, now we want to perform the binary search. So this is the main portion of this video, right? We have the left and the right. That means we have the left index and the right index. That means we have the entire range of that list. And this two values is going to keep changing until we find the mid value. So the first mid value that we're going to get is index 3, and that is because we are checking while left is less than right. So while the first index is less than the last index, we take the mid value as left plus right floor divided by 2. That means 0 plus 7 floor divided by 2. That means we get 3.5 right here, and the floor division will give us 3. So numbers mid, that means the numbers, or in this array, in this list, we have the name of the list is A, but here the name of the list is numbers. And the reason is because instead of using numbers, which is a bigger word, I just use one letter which is compatible, and it's basically the same thing, right? It's just the name of the list is different. Now we take the mid value, that is when we have received 3 as the mid value, right? Because on the left side we have 3 values, on the right side we have 4 values, but according to the floor division it gives us the value 3. So we use that 3 to check the target, and if that target, that is for index 3, which is giving us 4, if that is equal to the target, which is the search element, say if it is 8, it is not, right? 4 is never going to be equal to 8, so it's going to come to the else if block, and inside this we have the mid value, that is 4. We're going to check that number 4 if it is less than the search value or not. So we're going to check if the greater half, since it is sorted list, we're going to check if it is less than, that is if the search element is less than the search target. So if it is less than, we are eliminating the right portion of this, or rather the left portion of this list, right? And we're going to check only from the right side now. And notice here the while statement, that the right is always going to keep being constant and the left is going to keep changing, right? That means that since our element is on the right side of the list, the left will keep changing. That means we're going to keep eliminating the left side, okay, and it's going to keep halving that entire list. So we give left equals mid plus 1, that is 3 plus 1, so 4. So initially this was the mid value. Now the second mid value is going to be 4, right? So we're going to check, we're going to come back to the while loop, and we're going to check while 4 is less than equal to 7. So the next index is going to be 5. If 4 is less than 7, then we're going to check that we're going to change the value of the mid, that is 4 plus 7 floor divided by 2, which is going to give us the index 5. So now the mid value becomes 5, right? So initially our range was from index 0 to index 7, and the second iteration, while 4 is less than equal to 7, our range becomes from 5 through 9, right? On the right side we have the entire range at first in the first iteration. Second iteration, it is going to get halved from 7 or 8 values to down to 4 values, right? And then ultimately it comes down to 2 values. So how do we come in that way? Now we're going to check in the similar manner that when we're getting the index 5 as a mid value, that is the number 7, we're going to check if number 7 is less than or if it is equal to the target value, that is 8. If it is not equal to 8, it comes into the else block, that is this block, and it checks if it is less than. So since it is less than, we are going to change the left value, right? So it's going to be mid plus 1, that is 5 plus 1, which is going to give us 6. And then again we come through that loop again, and I'm going to check that 6 is less than 7 or not. And 7 is going to remain constant, right? And the value 6, ultimately we have the index 6. So this is going to be our next left value, which is 8 and 9. So we're going to change the value of the mid again with 6 plus 7 floor divided by 2, which is going to give us 6, right? So we have 6 now as the mid value. Now we're going to check if that mid value, that is 8, is equal to the target value, which is 8. So it does match, right? And if it is equal, then it just returns that index value, which is 6, which is the mid value, right? And like I said, we always have to come to this block, the if block, where the mid value is equal to the target. Ultimately, as soon as we found the search element, this block is always executed, but it executes anyways to check if the element that is to be found is equal or not to the list that we have, to the number that we have in the list, right? So ultimately this one always has to check. This is the final check where it is equal or not. So if we found the element, this is the last execution statement. After that, it does not even come to this block. So these blocks are basically used to check until this block is executed, until we found the element. And if we haven't found the element, it loops through this entire search algorithm, this entire list, and ultimately it returns -1. Why -1? Why not 0 or any positive integer? Because 0 and any positive integer is still in that index, is a valid index, but -1 is an invalid index. So that index doesn't exist basically. So if it doesn't exist, we just return -1. That means the number was not found, right? And then finally, the binary search that we either is going to give us a -1 integer, which is going to return an integer, or it is going to give us a valid integer that is going to give us the index of that found position, that the mid value, right? And ultimately we are going to store that integer in the result. And finally we are going to say that the sorted list is the list that we have sorted from the isSorted function or method, and we're going to check if the result that we have right here, if it is -1 or if it is not -1, then we found the position at so and so index, otherwise the element was not found. So if I do a run on this on the terminal, asks us to enter the separated by space the list. So I'm going to give an unsorted list first. Okay, I'm just going to paste that there and enter the target number. So initially I want to search 8. Okay, the list was not sorted, right, like we have here. the list was not sorted, so it is sorting right now, and it follows to the Tim sort algorithm to sort that element and show that the final sorted list is so and so, right? The same list that we have on the left on the right hand side that we see in this algorithm, and it gives us the index 6 or the position 7. That means that index 6 or the position 7. Index means it starts from 0 and the position means starts from 1, right? So that is the way we find the particular element using binary search, which reduces our time complexity, right? And if we are giving a sorted list, I'm going to run that again, give a sorted list. So this time it shouldn't sort for us, right? And it should not pass through this. It's just going to jump out of this entire thing. It's going to check, and if it is already sorted, it's just going to jump out and say that the list is already sorted. So in this way, I am going to search for the search element 2, say. The list is already sorted. This is the sorted list, and the index position is at 1 or position 2. So in this case, it is at index 1, and the position is at first and second position, right? So let's speak on the time complexity of the algorithm as to how much time it took to execute this. Now, why is binary search so fast? Because after every comparison, we discard half of the list, right? For example, 1000 becomes 500. From that 500, it becomes 250. From that 250, it becomes 125. And then from 125, 62, then 31, and so on, till we find that mid value, right? So the data set shrinks exponentially. That is why binary search has the time complexity of O of log n. The algorithm does not visit every single element. It keeps dividing the problem size repeatedly until the target is found. So when does O of log n appear? So like for example, where we have this binary search, while left is less than equal to right, we find the mid value, right? So for every iteration, it removes half the search space. So that means n, where left to right is the value of n, we consider that, and we are choosing the average of this entire list, right? So n becomes n by 2, and then n by 4, n by 8, n by 16, and then so on until we finally get 1, right? So that one is basically the mid value, the target value. So that is logarithmic reduction. So that is it for this video. And now that we understand how binary search works, we should start using this algorithm whenever we work with sorted data, because it drastically reduces the time taken to search for elements compared to linear search, where linear search uses each and every single element to search for it, and that takes more time. Whereas binary search, it reduces the time by searching on eliminating half that result in each and every single iteration. So I'm going to come up with more such videos based on data structures and algorithms. Binary search was one of them. And till then, keep practicing, and I'll see you on the next one.